far in our course, we've examined two of the three principal types of residential structural systems: bearing wall and heavy timber frame construction, traditional forms that have been in use for thousands of years. Now we'll look at the third, light wood frame construction, which has dominated residential construction in the US from the mid-19th century until our own day. The modern version of light wood frame construction is often called the platform frame, and in North America, this form of residential construction has been so ubiquitous for so long that it actually has seeped into our popular culture. Consider the classic 1939 movie, The Wizard of Oz. Even if we don't fully understand how a platform frame structure works, we find it entirely plausible that Dorothy's house could be plucked up off its foundation by a tornado and tossed through the air fully intact to the land of Oz. The more recent Pixar film Up capitalized on our conceptual familiarity with the platform frame in much the same way. It's doubtful that a British or German homeowner living in a masonry bearing wall or heavy timber framed house could possibly understand these movie scenes in the same way that we do. Today, we'll explore the platform frame dwelling, not as a cultural artifact, but as a highly refined technological system, a standardized but flexible arrangement of lightweight modular floor platforms, wall panels, and roof trusses that carry load efficiently and are well suited for the integration of the various building subsystems that we'll be discussing later in the course. Now, when I say that this system is highly standardized, I'm not exaggerating. 7 chapters of the International Residential Code are largely devoted to detailed specifications governing every aspect of the platform framing method. And most of the remaining chapters address the integration of electrical, plumbing, HVAC, and building envelope systems within a platform frame structure. Standardization of the method is also greatly facilitated by standardization of the associated materials. Throughout the US, lumber is sold in standard sizes: 2x4, 2x6, 2x10, and so forth. And by the way, these are only nominal sizes. The actual dimensions of these pieces of lumber are always somewhat smaller. The 2x4, for example, actually measures 1.5 inches wide by 3.5 inches. The 2x6 measures 1.5 by 5.5 inches. All commercially sold lumber also receives a standardized quality rating recorded as a stamp, like this one, on each piece of wood. Among other things, the stamp tells us the species of wood, this one happens to be white fir, and the grade of the board. Now, the highest grade with the fewest defects and thus the greatest strength is called Select Structural, or SS. The remaining 3, grades 1, 2, and 3, have progressively more imperfections and lower strength with each higher grade number. This one happens to be grade 2. Now, we'll see how these quality grades influence the design of a house in just a few minutes. To help you understand what platform framing is and how it works, I'll be using a computer model to build this hypothetical single-family home from the ground up, much as your contractor would do the job. With its 2 stories, full basement, and gabled roof, our hypothetical house has all the key structural features necessary to illustrate the major elements of a platform-framed system. And my model is architecturally simple, so we won't get lost in superficial details and complexities that aren't really essential to your understanding. Now, it's important to recognize that even though platform framing is highly standardized, variations on the theme are nearly limitless. For example, a foundation might be made of a concrete block or solid concrete. A roof structure might use rafters or trusses. Platform framing can even be implemented in steel for enhanced strength, fire resistance, and protection against insect damage. In my hypothetical example, I'll focus primarily on tried and true techniques and technologies that have been in common use for the past few decades. But I'll also point out some of the new technologies that are becoming increasingly popular on residential building sites today. So grab your tool belt and your building code and let's get to work. We'll start by surveying the building site and marking the locations of the foundation walls with wooden stakes and string lines. Guided by this survey, an excavator uses its hydraulically operated arm to dig the foundation excavation with great precision. Next, at the bottom of the excavation, wooden formwork is constructed for the wall footings and 2 interior column footings. A bed of gravel is placed at the bottom of these forms, and then the concrete is cast. Here in this image, the builder is using an alternative method, placing concrete directly into a precisely cut trench without any formwork. Note that before the concrete sets, a 2x4 board is pressed into the upper surface of the footing to create a slot, which will ensure a strong mechanical connection between the footing and the concrete wall that we'll be building next. Now, foundation walls can either be built up of concrete blocks, as you see here, or they can be solid concrete, cast in a single pour. We'll use the cast concrete alternative for our project. After the footings have cured, wooden wall forms are set in place and very heavily braced to withstand the very substantial outward pressure that will be generated by the wet concrete. A grid of steel reinforcing bars is then placed inside the forms. Now, in modern practice, particularly for the construction of housing developments with large numbers of similar foundations, reusable steel forms like these are often used as an alternative to wood. In either case, the forms are set such that the top of the foundation wall will be at least 6 inches above the final ground level, so that the wooden structure above will be less susceptible to rot. The concrete foundation walls are now cast using special inserts to form these pockets, which will eventually support a steel girder. Before the concrete sets, steel anchor bolts are embedded into the top surface of the walls at regular intervals. These will provide the structural connection between the foundation and the wooden frame above. Once the concrete is cured, the forms removed, we have a beautiful, solid foundation wall. Note the anchor bolts here and the pocket for the steel beam here. Here the steel girder is in place, and one of 2 steel pipe columns is being prepared for installation. The columns will be bolted to these footings below and to the beam above. By the way, the term girder refers to a main beam that supports other smaller beams or other structural elements. And indeed, that's precisely what this girder will do, as we'll see momentarily. Now, in this photo, note that a bed of gravel has been placed over the entire basement floor to provide a base for the concrete floor slab. Before pouring the slab, we put down a sheet of polyethylene plastic, a moisture barrier that we'll be discussing next lecture, and then a mesh of steel wire reinforcement. Finally, with a 3.5-inch thick concrete floor slab in place, our foundation is complete and ready for construction of the first floor platform. Of course, many homes in the US don't have full basements. The basement might be excluded from a residential design to save money, or more likely because of potential problems with water infiltration. In such cases, a slab-on-grade foundation is the most common alternative, though certainly not the only one. Construction of a slab-on-grade is quite similar to that of a full basement, except obviously it's not as deep. Footings are still required under all load-bearing walls, and in northern regions, the base of these footings must be below the depth of frost penetration. This practice prevents foundation failure due to a phenomenon called frost heave, the upward swelling of soil caused when water within the soil freezes and expands in the wintertime. In the northeastern US, where I live, the depth of frost penetration is about 4 feet. Given this depth, substantial concrete walls are still required to bring the top of the foundation up to ground level, even for a slab-on-grade type foundation. The concrete slab is then cast within these walls to establish the ground floor. Foundations are always built underground, not just to provide protection against frost heave, but also to enhance the strength of the underlying soil. Now, to see why this is so, let's do a simple demonstration. What I'd like to do is a strength test with these 2 equal quantities of sand. I'm going to dump the contents of one container out into this pan. And then I'm going to use this dowel as a simulated building column. So now envision the entire weight of the building pushing down on this column, and the column being supported on the soil below. As I push down on the column, watch how easily the column penetrates down into the soil. That penetration is possible largely because as the column is forced downward, it displaces the soil in the outward direction quite easily. Now I'm going to take the same column and apply load to it in my second batch of soil, but in this case I'm going to leave the soil in the container. And notice that now when I press down on the column, again simulating the weight of the building above, I'm unable to budge it. I can't cause the column to be pushed down into soil more than about 1/8 of an inch. Why the difference? Well, clearly the difference between these two cases is that in the second case, the plastic container provides lateral confinement. It prevents the soil from spreading out sideways as the column is being forced down into it, and that provides a considerable amount of additional load-carrying capacity as a direct result of that lateral confinement. Now, when a foundation is built below the surface of the ground, the surrounding soil provides just this same sort of lateral confinement, and thus substantially increases the soil's load-carrying capacity. Now, returning to our computer model, we'll build the first floor platform, the structural subassembly that actually gives platform framing its name. We begin by bolting a wooden sill plate to those anchor bolts protruding from the top of the foundation walls. This is the base on which the entire platform frame will be assembled. And if it seems excessive to have 30 or so steel bolts attaching the house to its foundation, just remember the Wizard of Oz, and remember too that truth can be stranger than fiction. The floor platform is constructed of parallel beams called joists, usually spaced 16 inches apart. This board, called a rim joist, caps the joist's outside ends and holds them in a vertical orientation. At their inner ends, the joists are overlapped above the central girder. And here we see the structural purpose of that steel girder. Without it, the joists would have to span the full width of the house. This would require huge timbers that would be prohibitively expensive. But with the girder in place, the joists span only halfway across the foundation and thus can be made of inexpensive 2x lumber. By the way, this girder will ultimately carry nearly half of the total weight of the house, so it needs to be strong. That's why it's made of steel, or alternatively of a very hefty wooden beam. Now, here's an actual floor platform under construction. The sill plate, the joists, and the rim joist, all held together with the code-specified number of nails. The yellow material on the outside of these foundation walls is insulation, which we'll be discussing in a later lecture. Now, wherever there are large openings through the floor, for a stairwell, for example, elements called trimmer joists and headers are added to frame the opening. And now we can install the structural subfloor, made of plywood, or possibly of its more recent alternative, a material called oriented strand board, or OSB. OSB is fabricated from random wood fibers glued together under high pressure, unlike those discrete laminations used in plywood. Now, these 4x8 sheets are nailed onto the tops of the joists and headers in a staggered pattern like this. If the carpenters have done their job well, the subfloor panels will line up perfectly with the joists, so very little trimming is required. Now let's pause from our construction project and investigate how this floor platform functions as a structural system. A wooden joist must be designed to prevent 3 fundamentally different modes of failure. First, the wood that's used to make the joist can physically rupture under the load. Now recall that a joist is really just a type of beam. It carries load in bending, experiencing compression on the top and tension on the bottom. Thus, this joist will fail if the wood exceeds its compressive strength on top or its tensile strength on the bottom. Now, with respect to this failure mode, structural theory says that a beam is significantly more structurally efficient if it's tall and narrow rather than short and wide. This particular wooden beam has a rectangular cross-section, so it actually provides us with a wonderful opportunity to test this theory, to determine whether in the vertical orientation it's stronger than in the horizontal orientation. Now, to run a test like this, I really just need 2 things. 1, I need an apparatus capable of running the test on, and 2, I need a load to apply to the beam. Well, there happens to be an apparatus right here, which I can use to place my beam on a pair of supports that allows it to span a fairly substantial gap of 4 feet. And now all I need is a load. Well, in the absence of anything else, let's use me. I'm going to mount this platform. And from this point, I'm simply going to cross the bridge to determine whether or not that beam in the vertical orientation is strong enough to carry my weight. So let's give this a try. Well, as you can see, the beam in the vertical orientation is indeed significantly strong enough to be able to carry my weight. Now let's repeat the test, but let's turn the beam 90 degrees into the horizontal orientation and see how well it performs in this mode. Once again, I will mount the platform. We have the same beam, the same load, and the only difference between these two experiments is that now the beam is in a horizontal orientation. Once again, I'm going to apply the load. Well, in this case, clearly the results are significantly less favorable. So why did this beam fail? Well, there really are only two possibilities. Either the compressive stress on the top surface of the beam exceeded the compressive strength of the wood, or the tensile stress on the bottom surface of the beam exceeded the tensile strength of the wood. Either way, the rupture of this beam precipitated the catastrophic collapse of my structural system. So that's the first failure mode. Now let's look at the second. Even if a joist doesn't physically break, it can fail to perform its intended function if it bends excessively. This is called a deflection failure. And once again, a tall, narrow beam is more advantageous with respect to this failure mode. So here are two identical wooden beams. And once again, I'm going to place one in a horizontal orientation and one in a vertical orientation. And in that orientation, I'm going to place them on my structural supports here. Now I'm going to add an identical load to each one of these two beams at the center. And what we can see very clearly is that with respect to the deflection failure mode, the tall and narrow beam is far superior in terms of structural efficiency. The vertical one bends much less than the horizontal one. Now, the third possible failure mode is a very complex phenomenon called lateral torsional buckling. And once again, I'll use this model to do a demonstration. I'm going to take two beams of slightly longer span. And this time, I'm going to mount both beams in the vertical orientation to represent the joists in a typical floor system of a platform-framed structural system. And I'm going to add a little loading platform out here in the center just so we have something to put these weights on. And now I'm going to add weight to this pair of joists, again, which are oriented in the tall and narrow orientation. I put one load in place, and things seem all right, but you may have noticed as I applied the load, there's a little bit of a tendency of this system to vibrate laterally. Some instability is developing as a consequence of this loading. When I add the second weight, that instability gets considerably greater. Now, we can see that the joists are starting to tip sideways a bit and kick out laterally. When I add the third, you'll see the lateral torsional buckling failure mode in action as the excess load causes the beams to kick out sideways, twist, and fail in both twisting or torsion and buckling, resulting once again in a catastrophic collapse of the structural system. Now, if lateral torsional buckling is allowed to occur, it greatly reduces the potential load-carrying capacity of the joist. Ironically, the very characteristic that's so advantageous with respect to the other two failure modes is highly disadvantageous here. Tall, thin beams are very susceptible to lateral torsional buckling. Short, wide ones are not. But as we've seen, a short, wide joist is highly inefficient with respect to the other two failure modes, rupture and deflection. So the best way to maximize the structural efficiency of a floor system is to use these tall, narrow joists and then to brace them laterally so they can't undergo that lateral torsional buckling failure. In older homes, these two techniques, called bridging and blocking, have generally been used to achieve this goal. Bridging and blocking are both effective in preventing joists from twisting, but installing them is labor-intensive and therefore expensive. Now, in recent years, builders have found that the same beneficial effect can be achieved at much lower cost simply by using a sufficiently strong structural connection between the subfloor and the joists. So, to demonstrate this point, I'm going to add this subfloor to the top of these two joists that just failed by lateral torsional buckling a moment ago. Now, my subfloor is actually just made of balsa, so it's very weak and very flexible. It's not going to add a significant amount of strength to the beams. And I'm actually not even going to make a rigid attachment between the subfloor and the joists. I'm just going to insert them into these two slots on the bottom. So let's give it a try. Put my subfloor in place. And now I'm going to apply exactly the same amount of load that caused the lateral torsional buckling failure a moment ago. And with those three weights in place, there's absolutely no tendency to fail. This structural system is both strong and stable, and that stability has been attained specifically because of the connection between the joists and the subfloor. And because of that connection, these joists don't buckle, and so their full bending strength can now be realized. So how are these floor joists actually designed? Well, if the platform framing system weren't so thoroughly standardized and institutionalized, an engineer would need to perform a series of fairly complex calculations to determine load effects, bending strength, and maximum deflection. But as we've learned, this sort of engineering analysis is almost never required in residential construction because the engineering has all been incorporated into our building codes. To see how this works, let's actually design the joists of our first floor platform on our hypothetical house. The structure measures 32 feet wide, and the steel girder divides this width in half, resulting in a span of 16 feet for each joist. The joists are spaced 16 inches apart, though I could have used either 12-inch or 24-inch spacing as an alternative. Now let's refer to the International Residential Code, Chapter 5, which governs floor systems. I've extracted this maximum joist span data from a larger table in the code. The full table covers many different design alternatives. My extract addresses only the design parameters that are relevant to our project. A code-specified live load of 40 pounds per square foot, dead load of 10 pounds per square foot, a reasonable estimate for a living space that doesn't have unusually heavy finishes, like stone floor tile, for example. Our joist spacing of 16 inches, and an assortment of different wood species and grades. Now let's assume that my local lumber yard has a good supply of Douglas fir in various grades. If I choose high quality but expensive select structural lumber, the smallest joist that will span 16 feet safely is a 2x10. Its maximum span is actually 17 feet 8 inches, but the next smaller joist size, a 2x8, will span only 13 foot 7 inches, so it won't work. Well, what if I use less expensive grade 1 Douglas fir? Well, in this case, a 2x10 joist is still the optimum solution because it will safely span 16 feet 5 inches. Clearly then, the cheaper grade 1 lumber would be a better choice than the select structural lumber. So, if grade 1 is good, might grade 2 be even better? Well, as you can see, a 2x10 made of grade 2 Douglas fir will span only 15 feet 7 inches safely. So we would need to use a 2x12 for our 16-foot span. Also note that for grade 3 Douglas fir, the largest available lumber size, a 2x12, will span only 13 feet 10 inches, so we can't use this grade at all. So now, to finalize our design, we only need to compare the costs of our two viable alternatives, a grade 1 2x10 and a grade 2 2x12. The cheaper of those two is our optimum choice. And thanks to the code, we were able to make that choice without a single engineering calculation. Now, returning to our computer model, we can now backfill the foundation excavation with compacted soil. We didn't do this sooner because the lateral pressure of the soil might have tipped the foundation walls inward. Now, with the first floor platform installed, there's no danger of this happening, so we can proceed with construction of the first story exterior walls. In a platform-framed structural system, each wall is composed of parallel studs, typically 2x4s spaced 16 inches apart, nailed together with a sole plate across the bottom and a pair of top plates above. At the top of each window and door is a solid wooden beam called a header, which we'll discuss in a few minutes. Now, these wall panels are usually assembled horizontally, lying on the subfloor that we just finished installing. Once a wall is fully framed, it's tilted up and into position along the edge of the floor platform and held in place with temporary diagonal braces. After all walls are erected and their alignment has been carefully checked, they're nailed permanently into position and then covered with sheathing made of plywood or oriented strand board. As we've seen, most houses are too wide for floor joists to span safely from one outer wall all the way out to the other. Thus, one or more load-bearing interior partition walls are nearly always required in the framing plan. This wall serves the same structural function as the steel girder below the first floor, except the load-bearing wall supports only loads applied to the second floor and above. Most houses also have non-load-bearing partition walls, which subdivide the interior space but don't support the floor above. These walls usually aren't erected until after the next floor platform has been added overhead. So now let's pause and examine these wall panels as structural entities. Typically, a wall panel must carry both gravity loads, consisting primarily of dead, live, and snow load, and lateral loads caused by wind or earthquakes. So gravity loads are carried downward through a wall by the studs, acting in compression, like this. Wherever a stud happens to be interrupted by a window or door opening, this header picks up the load in bending and transmits it out to the adjacent studs, where the load then resumes its normal downward path. Now, the principal failure mode of a wall stud is buckling. That's this tendency of any structural element in compression to fail catastrophically by kicking out sideways like this. As you can see, long, slender elements are much more vulnerable to buckling than short, stout ones. And because 2x4 wall studs do tend to be relatively long and slender, buckling would seriously limit the strength of this typical wall panel, except for the sheathing, which does a wonderful job of strengthening the studs by preventing them from kicking out sideways under compression, primarily as a consequence of the row of nails, which connects each stud to the sheathing rigidly and provides the sort of structural connection that prevents the studs from buckling sideways. Thus, wall sheathing strengthens studs in exactly the same way that the subfloor strengthens floor joists. So what about lateral loads? Well, here the rectangular geometry of a wall panel is problematic because it's highly susceptible to shearing. That's this distortion of a rectangular panel into a parallelogram shape when it's loaded horizontally. Now, in an earlier era, this problem was addressed with diagonal braces like these, which were let into the studs and rigidly attached like this. And these braces are quite effective. They stabilize the wall panel in the same way that diagonal braces stabilize a heavy timber frame. But as with timber framing, installing these custom-fitted braces takes time and money. And so it's hardly surprising that in recent years, this method of resisting lateral loads has been replaced by a simpler technology. And as you might have guessed already, that simpler technology is modern structural sheathing panels, which have proved to be quite effective in resisting shearing, like this, as long as those panels are solidly attached to the studs, to the sole plate, and to the top plates with the code-specified number of nails. Now, returning to our computer model, we can now add the second floor platform, the walls, and the ceiling structure using exactly the same methods we used on the first floor. One of the most important advantages of platform framing is that this process can be accomplished without cranes or scaffolding because each new floor platform provides a solid working surface on which the builders can fabricate the next higher story. And finally, we'll add the roof structure, which consists of ceiling joists, a ridge board, and these angled beams called rafters covered with roof sheathing. So how do rafters work anyway? Well, this model shows us two pairs of rafters connected to a ridge board in the center and supported on a pair of top plates out on the ends. Under gravity load, when I push down on the center of this set of rafters, the rafters are going to tend to bend. And that's going to happen as a consequence of the fact that the ends are going to tend to splay outward, to displace outward under the action of the vertical loading. As that splaying occurs, the most severe bending of the rafters is going to occur right here at the center in this critical connection. Watch what happens. Not very effective. Well, to prevent this sort of failure, building codes require a strong structural connection between the outer ends of the rafters and the ceiling joists, located right here. The resulting triangular structure, called a truss, carries load in a fundamentally different way than the rafter system that I just destroyed. The joists now prevent the rafters from splaying outward, and as a consequence, we now find that the structure carries load in a different way, with the rafters carrying load primarily in compression and the joist carrying load in tension. This simple truss represents an extremely efficient system for carrying gravity loads while also providing the sloped roof surfaces that shed rainwater and snow as a component of the building envelope that we'll be talking about next lecture. Still, efficient as it might be, no aspect of platform framing has been immune from product improvements over time. In recent years, builders have begun replacing this simple combination of rafters and ceiling joists with these more elaborate prefabricated roof trusses, custom designed, factory built of astonishingly lightweight lumber and held together with these ingenious metal nailing plates. They create an amazingly strong joint, and that joint is assembled with considerably less effort than those precision-made mortise and tenon joints we saw in the heavy timber frame last lecture. Now, by code, these trusses must be designed by a licensed engineer, but the investment in design clearly pays off in greatly enhanced structural efficiency, particularly for multi-home developments that might require hundreds of identical trusses. Well, now that we've erected a complete platform frame structural system, I think you can see not only how it's built, but also how it carries load. Snow load is applied to the roof sheathing, then transmitted through the trusses to the exterior walls, then down through the wall panels, foundation walls, and footings into the soil below. Simultaneously, live load is applied to interior floors, then transmitted through the joists to both the exterior and interior walls, with the interior load path passing through a steel girder, interior columns, and column footings before finally reaching terra firma. And wind and seismic loads are carried by the wall panels themselves. This beautifully engineered system has flourished through nearly 2 centuries of refinement, adaptation, optimization, and innovation for 3 reasons. First, it's highly economical because it uses lightweight, standard-sized lumber that can be worked with common tools and assembled with simple fasteners, because it can be erected without cranes and scaffolding, and because manufacturers have created thousands of products like windows, doors, electrical components, and insulation that have been purposefully designed for compatibility with it. Second, platform framing is a highly flexible system that can be applied to an incredible variety of architectural styles, from small and simple to grand and architecturally distinctive. But perhaps most importantly, it provides a solid framework for effective integration of the building's other engineered subsystems. In the next lecture, we'll examine one of these systems, the building envelope, and we'll consider its complex role in enclosing and maintaining the environment in which we live.